Bismillahirrahmanirrahim. Assalamualaikum and a very good day to you all. In this video, I'm going to talk about introduction to shear stress in beams, which is another topic, which is topic 3.11 in strictly mechanical engineering design. So the topic 3.11 is shear stress in for beams in bending. Okay. It's better you have the textbook with you. I hope this video can give you some additional knowledge. Okay. So this is the figures that you can find in the textbooks. Okay. So what is shear stress in beams? Okay, shear and bending forces in beams. Beams in engineering experience both shear force and bending moment affecting their structural behavior under load. Okay. So what does it mean? In simplest, you see the bridges over the river. Okay, the bridges over the sea, over the ocean. That kind of bridge. Okay, you imagine the bending force the come from the load, the motorcycle, the vehicles coming on the bridge is this it will give the bending force. Okay, where the comes the shear force on the bridge. Okay, the shear force come from the wave on the ocean. Okay, from the wave from the flow of current in the river. Okay, it will give the shear force. So this combination of force at the same time is it is called shear stress. Is related to this topic lah, which is shear stress in beams. Okay, so flexure formula assumption. The flexure formula assume pure bending for simplicity, yet can apply under combined shear and bending force for typical beam design. For example, simply supported beam under distributed load experience combined bending and shear forces along its length. Okay. So derivation of shear force, which is equation 3.29, you can find in the textbook. Okay, shear stress origin, shear stress tau. Okay, the symbol is tau, results from internal forces that vary with the position along the beam. Okay, in the beam, you can assume there will be neutral axis in the middle of it. Okay, okay, this is the position that we're going to talk about. Shear stress for calculation formula. For the formula, tau equals to VQ over IB, where V is the shear force, Q is the first moment of area, I is the moment of inertia, and B is the beam width. Calculate shear stress distribution. For example, rectangular beam. In the rectangular beam under load, shear stress peaks at neutral axis and decrease towards the edges in a parabolic shape. Okay. You can find it in this picture lah. You can see here in the beam shape in we become the parabolic shape. The beam shape in table 3.2 in the textbook. Also, I paste it here. It is a parabolic shape. You see the stress is at the middle one. Exactly at the at the neutral axis. It is the highest. Okay, and it gradually decrease towards the edges. Okay. And what does it mean? It You see here, peak shear stress at neutral axis, in particular beams, shear stress peaks at neutral axis, reducing variability towards the edges, meaning that uh, uh, if you cut it, if you cut the rectangular beam, you find it harder to cut at the middle one. Once you have cut the middle one, which is you cutting the neutral axis, it will become easier to cut. Okay. Neutral axis is the hardest to cut because the peak shear stress is at the middle of it. Okay. Whether you cut a tree, whether you cut anything, it will be find it hard to cut at the middle one. Okay, because the peak shear stress at the middle one. Okay, at the shear at the neutral axis. Okay, shear stress in varying cross section. Beams with varying cross section like I beam experience distinct shear stress pattern, especially along the neutral axis. Secondary consideration in standard beam, transverse shear stress is often secondary to bending stress, but can be crucial in thin wall section. And cantilever I beam with load. In cantilever I beam under concentrated load, both bending and shear stress influence structural integrity. Okay, that's all for the video right now. Inshallah, we meet in the next video. Thank you very much.